All right, let's take a look at week 5, assignment 3, IJKLMO. Let's see. We don't want to. You know what? I'm going to go ahead and start the timer because I think 10 minutes is just plenty of time for these videos. And seriously, I can't find my alarm thingy. Oh, great! It's on the second page now. All right. Well, now we're already probably 2 minutes into this video. Oh my god. All right, part I, gravitational potential energy. So an astronaut is lost in space. So they're dead. Okay, moving on. Just kidding. The moon is directly opposite the astronaut on the far side of the planet, in line with the center of the planet, the distance r from the astronaut. Mark an X on the diagram shown to indicate the location where the astronaut could move so that she would feel no net gravitational force. So the X is here close to the moon, right? We would need to be in between. So if we were in between the planet and the moon would be pulling to the right and the planet would be pulling to the left. And at some spot in between them, their pulls would balance and cancel each other out. And that spot needs to be closer to the moon than to the Earth because the pull of the moon is less because it's a smaller planet. Let's see what's going on here. Oh my gosh, there's hot oatmeal here. Woo!
There's much chocolate in it.
Perfect. Thank you. All right. If the planet was not between the astronaut and the moon, but the distance r was the same, would the gravitational, so the pull of the moon on the astronaut is related to the mass of the moon and how far away the moon is, or how far away the astronaut is from the center of the moon. That's not going to change just because the planet's not there, right? The gravitational forces, the gravitational force of the planet on the astronaut is independent of the gravitational force of the moon on the astronaut. They will add together to create a net force, but they don't affect each other, in other words. The astronaut's jetpack is powered by an arc reactor. Oh, it's Iron Man. So that's why they're not dead. And they want to travel to other parts of the solar system. Oh, it's magic. Consider the energy required to escape from the configuration shown above. If the astronaut was instead standing on the moon, it would require more energy because the force, so we're on the moon, so we're over here, right? So I guess we're still pretending there's no planet there, right? This force here that the astronaut feels is a lot less than the force the astronaut would feel standing on the moon, right? So the gravitational force that needs to be overcome to escape would be a lot more. The force of impulse force you would need to get off the moon would be a lot more if you were standing on the moon, whether or if you were this great distance r away from the moon. So you're going to need more energy to escape the gravitational attraction. So here's a lot of words. There you go. That's kind of what I said. All right. We're still on I. The astronaut is able to travel a very far distance x away from the planet-moon system at a constant velocity, needing a total amount of energy to do so. Why the jetpack wants to do work on the astronaut to maintain a constant velocity? The net force on the astronaut will always be pointed back toward the planet-moon system without an opposing force from the jetpack doing the work. The astronaut would experience acceleration. Right, so there'll always be a force pulling back on the astronaut. The astronaut's just going to keep getting pulled slightly by the planet system. So you have to have the jetpack pushing against that all the time in order to keep going. Otherwise, it's going to pull you backwards. The planet will. This is a graph of the force exerted on the jetpack. So it doesn't have to apply the same amount of force to keep you going. At the beginning, it's got to apply a lot of force, right? And then as you get farther and farther away, the pull of the gravity on you from the planet is less and less and less, exponentially less and less and less, because it drops off with the square of the distance. So that means the amount of force the jetpack needs to push on you also drops off with the square of the distance. So that's what this graph is showing us. It's 1 over r squared. Look, 1 over r squared, I got it right. I have a raisin stuck in my teeth. Ugh. I don't think I can continue. Describe the power required from the jetpack as the astronaut travels away from the planet-moon system. Well, less energy, less power. It takes less energy, right? It has to push less force out as we get farther away. Less force means less work is done. Less work is done means less power is used. And they have a whole nother explanation here, which is also valid. I like it. All right. Let's look at J, impact of mass on conservation of energy. An apparatus to determine the coefficients of friction is shown to the right. The box is slowly rotated counterclockwise, and the box makes an angle theta. The block of mass m just starts to slide, and at this instance, the box is stopped from rotating. Thus, at angle theta, the block slides a distance d, hits the spring k, and compresses spring x before coming to rest. Draw a qualitative energy bar chart that represents the energy of the block Earth beat bot doot baboot bot. Initially, what is it trying to tell me? It's trying to tell me that at the beginning, all the energy is kinetic. Okay, because I guess we're inside the box, and I guess because the system doesn't include the planet. And then as a displacement, as it travels down the box, it loses kinetic energy. It gains potential energy due to gravity, and some energy is lost due to friction. Okay, I'm not going to lie, this doesn't make any sense to me. I'm sorry. But you know, I guess I need to do some research on this question. I don't understand. I think it would. Why wouldn't it all be potential energy to start with, and then as it slid, some of it would be kinetic, some of it would be potential, some of it would be lost due to thermal losses, and at the bottom, it definitely would be all spring energy with even more energy loss. So the bottom, the last piece, that looks fine. I just feel like the first piece, I just feel like they put the bar in the wrong place on the first piece. I think that bar should be over potential energy due to gravity. But doesn't mean that I'm right. So if you can explain it to me, I would love that. All right, or you could at least validate my feelings. The second block is susceptible to the same conditions and block, same materials. Right, it would remain the same because the coefficient of friction, that's the whole experiment is about the coefficient of friction. And the coefficient of friction is related to the two surfaces. What are they made out of? How sticky are the two surfaces when they rub against each other? That's what the coefficient of friction tells us. Right, and it's a ratio of the frictional force divided by the normal force. Well, if you increase the mass, you increase the normal force, but you're also going to increase the force of friction, right? They're just going to increase by the same amount. Although mass doesn't impact the speed just before the block impacts the spring, it will impact the distance the spring is compressed. That will push it harder, won't you? So I don't even know, what's the question? It's on a different page. There is no question. Oh, new block, how the values would change. V would remain the same. I really thought they were talking about coefficient of friction. I'm sorry, I gave an explanation for the completely wrong thing. Well, it does say the coefficient of friction does not change. So anyways, what's happening here is the spring distance will increase because They have the same speed upon arrival. The 2M block will have more gravitational potential energy at the beginning. So it's going to give the spring more spring energy, which means the spring has to compress more. All right. Yeah, that's about 10 minutes. So let's go ahead and stop this video and start a new one for K. This would be IJ.